I am Martijn. In this video I will tell you something about the cross ratio. It is maybe the simplest geometric quantity that stays constant under projective transformations. It has been shown that any projective transformation can be expressed algebraically as a multiplication by a square matrix with a non-zero determinant. Well, in that case, the only invariant property of a single point is that it is a point. Well, that's not very useful, so that's why the cross ratio is more commonly used. So first I will define the cross ratio on the projective line to keep things simple. Then I will show you that this cross ratio is constant under projective transformations. And then I will show you a new definition that can be used on the projective plane. And I will show that this new definition is actually, well, it will result in the same quantity as the definition for the projective line. For the definition, we'll be making use of the determinant quite a lot. It has been abbreviated like this. And the cross ratio of 4 vectors is defined in the following way. Now, if we use these 2D vectors, this 2D space to support a projective line, we have that a vector spans a 1D subspace, and any non-zero vector in this subspace should represent the same point. As you can see here, multiplying a vector by any non-zero real number, this leaves the cross ratio unchanged. It's just a simple algebraic identity that you could actually pull out these non-zero real numbers. And on the right, because they are non-zero, they cancel each other, and we're back to the first definition of the cross ratio. So it's well defined for the projective line. Now we need to show that the cross ratio is indeed a constant under projective transformations. As we have stated before, this can be expressed algebraically as a square matrix with a non-zero determinant. In case of the projective line, it's a 2 by 2 matrix. If we now use this definition of a matrix R, the first equality over here follows. It's just another way of writing it. Remember that these square brackets represent the determinant, which shows here. Then a simple algebraic identity tells me that this determinant is equal to the product of these two. And then using our definition of R again leaves us with this. Now, filling this into the definition of our cross ratio, we will end up with this. And remember that for projective transformations, this determinant of M, it must be non-zero. So again, we can cancel these terms, and we are back with our first definition of the cross ratio. So it is indeed invariant under projective transformations. So now it's time to move on to the projective plane. We are still talking about an ordered set of 4 collinear points, these A, B, C, and D. But now we have added an auxiliary point O to the set, which is not on the same line. Our new definition is nearly equal, only now the determinants can no longer be 2 by 2, because points in the projective plane are represented by 3D vectors. So we start off with a wall of equations. The new definition is stated over here in the top. We actually have added only the point O to all these determinants. And following the same line of reasoning we used before, we can show that the cross ratio is well defined for projective points, so that we can multiply them by any non-zero real number and the cross ratio is still the same. These numbers are non-zero, so we can cancel them. The same goes for projective transformations. We are now talking about the projective plane, so a projective transformation is a 3 by 3 matrix with a non-zero determinant. Then we can apply this equality. We use a new definition for R with these points. This is just the same, and here the same algebraic identity we used before, and then this definition is, well, it's just a different way of writing this. And so we can see that the cross ratio of the transformed points is still the same, because the determinant cancels, and well, the cross ratio is just this again. Alright, now we need to show that this cross ratio will result in the same value as the cross ratio defined before. For that we need some pictures. Okay, here we see the projective plane. I've indicated it in green. It's the z=1 plane. It's a little square here, but of course it goes on to infinity. Two vectors a and b cross the projective plane over here and once more over here. Let's try to indicate it with little crosses. And together these vectors, they span another plane indicated in red with the normal vector a cross b. The intersection of this red plane with the projective plane will result in a line. It's green over here, and this line goes through the projective points a and b, and any point on this line can be expressed as a linear combination of a and b, because any vector crossing this line can be expressed by a combination of a and b, simply because this vector has to be in the red plane, and any vector in the red plane can be expressed as a linear combination of a and b. So we have shown that points on a projective line can be expressed as a linear combination of 2 points spanning the line, and also we have shown that the cross ratio is invariant under projective transformations. So we can use this information to think of a smart projective transformation. It's expressed over here. We project the points to the following new points, and using that the points C and D are also on a line spanned by A and B, we know that these points must be a linear combination of A and B transformed. So they look like this, and well, we can think of this projective line as simply a projective line supported in a 2D space, because all the z vectors are 0 for the points of interest. We redefine these points by their 2D coordinates, and we can show the following equations. The cross ratio is equal to the cross ratio of the same points transformed projectively. The definition of these points is filled in over here, and we can see that the determinants all collapse to 2 by 2 determinants, and that they are actually equal to these determinants, which was defined before. So now we can see that the cross ratio we have defined for our 3D points has the same value as the cross ratio defined for 2D points, for points that correspond to each other. Well, that's what I wanted to show. Thank you for watching, and goodbye.